Yeah, excellent. So thanks, it's a great pleasure to give a talk in this conference. So yeah, so my talk will be, part of it relatively basic. I wanted to introduce some of the ideas of GEG and hydrodynamics, and I think there will be other talks that will discuss these things a bit more. So basically the see this work. The main, so it's going to be a bit conceptual and kind of trying to get the ideas right. So the main question here that is at play is the question of emergence. A lot of the talks in this conference deal with that. So we have a lot of particles in interaction, some perhaps simple microscopic interaction, and at large scale, something new emerges. For instance, some new question of hydrodynamics, superdiffusion, and all these things. And the question is, how do we extract these emergent behavior at large scale? This is kind of a very fundamental question in theoretical physics. And beyond. Okay, so the plan of my talk is going to be, well, I'm going to review some of the old paradigms of emergent equations in many-body systems, some stuff that you will find in the standard textbook, and then present a slightly different viewpoint and show principles of hydrodynamics that allow us to go a bit further. Okay, in particular, would allow us to go to generalized hydrodynamics for integrable systems, so a bit of an overview of that, to introduce at least the main concepts for the conference. And what I would like to show as a new result, kind of recent result with my collaborators, is how to deal with space-time dependent Hamiltonians all the way up to diffusive scale, so get very general hydrodynamic equations that generalized was being done until now in textbook. And that, in principle, should be accessible in modern experiments. Okay, so the old paradigms. Well, I mean, the very first one is the paradigm of what are the equations for a system of free particles. So suppose I have a system of a certain number of free particles with within some external potential W of x. Well, we know what the equations are for describing the system of particles at large scale. So if you look at the phase space of that system containing particles, you can gather your particle within phase space cells, and you know that the density on phase space is going to satisfy a very simple evolution equation, a conservation equation, which is equation for conservation of phase space elements. And since there's a force here, there's an external force that actually is a flow on phase space elements, right? So that's the equation. Actually, this equation is in fact an exact equation for these free particle systems. If you define your density in atomic fashion, so you follow the trajectories of particles, so the trajectories in phase space, position and momentum. Okay, so so this is a very simple equation, and perhaps if I do manage at the end of the talk, I'm going to get to an equation that generalizes this for more general external potential in integrable systems. Okay, so essentially that's kind of question we would like to generalize. Okay. Now, integrable systems are in general interacting. So if you have interaction, so if you have a system of particles with interaction and some external potential, for instance, then the equations that you will find in textbooks are completely different. Phase space elements are not conserved anymore, naturally. So what you will find in standard textbooks are the equations of hydrodynamics. So here I'm showing them in one dimension, but you can write them in higher dimension as well. And basically you write conservation of mass, flow of momentum, and some conservation of energy equation, which I have not written. Okay, so these are instead of having a function on phase space, you have just function on space, also depending on time, and you have essentially three functions, just two of which I have shown here. So the density of particle and the velocity, or rho times v, is going to be the density of momentum. Okay, and these equations are controlled by few parameters that know about the interaction, the pressure and the viscosity, and these kind of come out from the physics of this interacting system. So once you know how to calculate the pressure for that interaction and how to calculate the viscosity for that interaction, then you can write what the equation that emerge at large scale. Okay, so this is very nice, but it is helpful to write this equation more in a conservation form, like the conservation of phase space element, right? So one way that you can write that is by introducing the diffusion matrix. You write this equation as conservation of density with its associated current, and the current here receives a contribution both from some part which does not just depend on the density, some part which depends on the derivative of the density, in order to be able to get the second derivative term. So the second derivative term is the one that knows about the viscosity of the fluid. Okay? So if you just kind of look at these equations and want to write it in this conservation form, you immediately identify what the quantities should be. So there's a density of particle, there's a density of momentum, which is v times rho, which is the same things as the current of particles. And there's a pressure, which is related to the current of momentum. And your diffusion matrix, you read it off, and it has, that particular form. It knows about the viscosity, and the force term knows about the external potential. Okay? So this is, if you write it in that general form, your conservation equation. In fact, this form, this particular way of writing these various terms come out from Galilean covariance, actually. So this is something that you can write, and in the end, all you need to evaluate are the pressure and the viscosity. Okay. So now it is convenient, actually, so kind of massaging a little bit more this very standard equation to rewrite it in terms of an Onsager matrix. So to actually introduce some statistical mechanics in this equation. So this is an equation that you can find that, of course, earlier wrote an equation like that from a long time ago without knowing about statistical mechanics. But now we know about statistical mechanics, and Boltzmann told us, well, you have to consider your system as being composed of many particles and all that. And that actually gives some conditions and some constraints on the kind of equations of hydrodynamics that we can write. Okay? So what you can do is to change your thermodynamic variables to the external potential of statistical mechanics. So you write your densities and currents in terms of average in some give state. So in the current system that I'm showing, there's just three conserved quantities. There's the energy, the momentum, and number of particles. So that's your give states. And it turns out that you can write indeed, of course, you can change variable from densities to external potentials just by writing your densities as an average in a give state. And the current Ji that was written here, this J0 and J1, comes out by writing these current of particle and momentum in that same give state. So it turns out that this bit of the equation is actually a bit that knows about the give state. And so you can form the susceptibilities once you have these give states. And in the end, if you write your second derivative equation in this variable in terms of these other variables, these betas in terms of q's, just a change variable, you introduce what is called the Onsager matrix, introduced by Onsager originally a long time ago, which is the diffusion matrix times the matrix of susceptibility. This Onsager matrix brings out a lot of the physics impact of this diffusive scale equation, because Onsager matrix, what it encodes how the currents react to external forces. And what's actually happening in this equation is that these currents react to some forces. Well, here is not external force, but it's a force due to internal pressure in the system. This Onsager matrix was studied by Onsager some time ago and has a very, very nice physical interpretation and some important property. Okay, so what are what is this physical interpretation? Well, essentially, Onsager matrix can be obtained by looking at how a current varies if you change an external force. So you imagine a system. So you forget about hydrodynamics, imagine a system, put an electric field in there and change a bit the electric field, the current of electron will change, right? So Onsager matrix tells you essentially how this currents will change if you change external fields and external forcing, okay? And you can calculate that by standard perturbation theory. You get an expression for this Onsager matrix. And once you have this expression, so it turns out is indeed this particular concept is the one that is involved in the hydrodynamic equation. So that gives you a way of calculating so that matrix, and in particular the viscosity. So the properties of these hydrodynamic equations, the emergent properties of at large scale, can be calculated from basic properties of your many body system. What you have to calculate is a two-point function of currents in a statistical state, okay, in a state such as the Gibbs ensemble. Okay, so it involves something called the KMB inner product, but essentially it's just a two-point function of connected two-point function of currents. Okay, you have to evaluate that at large time and subtract the large time behavior, large time limit of that space integrated correlation functions. So that's some detail. So one of the things that Onsager noticed actually from this is that by time reversal symmetry, this Onsager matrix satisfies the so-called Onsager symmetry relation. What it says physically is that if you have a force due to a certain field, so electric field, JA, so electric field, so corresponding to force V, and you will see, you look at how this force acts on some other current, I don't know, like thermal current, energy current, JA. Well, it's the same thing as putting a force on the energy and seeing how this influences the electric current. So there's this symmetry, and that's one of the most fundamental relation in non-electrical physics, the Onsager symmetry relation. And it's a relation that gives some constraints on the hydrodynamic equation in general, and that allows it to have good properties, in particular, production of entropy and reaching of thermal state. Okay, so this is kind of an important relation that comes out from statistical mechanics. There are other relations similar to that, in fact, even at the earlier scale. So before you go to the Onsager matrix and the second derivative term, there is a similar Onsager symmetry relation, which was discovered much later, not by Onsager, which tells you that the variation of these currents, so the currents that appear as calculated in Gibbs state, with respect to Gibbs potential, are also symmetric. And these two relations actually give the diffusive hydrodynamic equations all the good properties that one would have to have for a diffusive equation. Okay, so this is kind of the stuff that is relatively well known that you can find in textbook. But what I would like to say is that, in fact, these principles, so the principles that are at the basis of these equations, are valid for almost any, so I'll put any in quote here, almost any many-body system with short enough interactions. Okay? So quantum or classical, integrable or not, in general leading to multi-component hydrodynamics. In particular, they are even valid for the free system. So the system I wrote to you in phase space, where you have conservation of densities in phase space. In fact, these equations are nothing else but the general equation of hydrodynamics as applied to free systems. So essentially, this I there that counts the conserved quantities, like conservation of mass and energy and momentum, they become conservation of elements in phase space. That becomes a P, essentially. So there is a general set of principles that allows you to put all of these on the same footing. Okay? So there is the general idea of hydrodynamics allow you to explain with the same set of principles both of these type of systems that I've described. So free models and interactive models, and integrable models go in between these two things. So that's kind of the main set of ideas. Okay. Another thing is that actually these equations that I've shown, which come from standard textbooks, are actually in general incorrect. So if you have external forcing of a general type, is where you have external field coupling to various conserved quantities. In fact, there are additional terms that appear there, which are also of diffusive type. Okay? And we've calculated these terms recently, and that's what I'd like to get to. Essentially, that kind of will allow me to generalize this to integrable system with external potential. Okay? And another thing actually that is interesting, which we found, but I will not explain too much, is that in all these application of general principle to get to describe hydrodynamics, one of an important symmetry, which appears to be the fundamental symmetry for having the right properties of hydrodynamic equation, is not really time reversal symmetry, but rather PT symmetry, so parity time reversal symmetry. In particular, the symmetry of the Onsager matrix, which is at the basis of a lot of non-equilibrium physics, is a consequence of PT symmetry and not only time reversal symmetry. In fact, a lot of nice property of the diffusive scale hydrodynamic equations are consequence of PT symmetry. Okay, so what I'd like to describe now is the first 2 points essentially. So the first point leading to the equation of generalized hydrodynamics for integrable systems, and the second point leading to, well, these equations in generic external fields, so Hamiltonians that vary in space. Okay. So let me start with the first point. So the first idea, at least, so first, without diffusive scale, so just purely at the earlier scale, without taking into account the second derivative, is the idea of local thermalization. So the idea here is that you have a microscopic system where the density of particles is different, depending where you look at, and various other quantities, momentum, and all that are different depending where you look at. And you construct these mesoscopic cells where you assume or hope or you observe physically that there is some kind of relaxation going on, and the state within these fluid cells goes to some kind of reduced set of states, for instance, the Gibbs states or the generalized Gibbs ensemble. Okay. And the question is to describe the evolution of these local fluid cell where relaxation has happened. Okay, so that's the basis of hydrodynamics, at least at the earlier scale. Okay, so in equations, you have some conservation laws which allow you to construct total conserved quantities and Gibbs ensemble, like I've shown in the previous slides. And the assumption of hydrodynamics is that if you evolve any local observable in space-time large enough in space-time, for large enough space, large enough time, with an initial state which varies on large enough scales, what you should observe is that your observable is just calculated within a locally relaxed state where the relaxation has brought down the number of degrees of freedom to only a few external potentials associated to the conserved quantities. Now, a few can be a lot depending on the number of conserved quantities, but basically you reduce your degrees of freedom to potential associated to conserved quantities, so to the conserved quantities essentially. And once you have that, then you write the conservation law for your conserved densities and currents, and this is the earlier scale hydrodynamic equation. So without the diffusive term, without the viscosity, and here without the force. Okay. So it is important to say that these equations are expected to be very general. So you do not need to have chaotic dynamics in order to get to such equations. Okay? You just need to know what are the possible generalized Gibbs ensembles or the possible relaxed state, because these states depend if you have chaotic dynamics or integrability or whatnot. But once you know what is the set of states, then you can write these equations. Okay? And in particular, in free models, you can write these equations where your set of states is described as a arbitrary distribution in phase space. So, or arbitrary distribution of momenta. Okay? So, yeah, okay. So this is the general set of equations that you get for supposedly for a large set of many-body systems. Okay? Let me just skip that actually. So in generalized hydrodynamics, we use these ideas essentially and apply that to the context of integrable systems. Now, integrable systems are very much like free systems, but they are also like interacting systems. So they are very much like free systems because there is a large space of conserved quantities. Okay? So the basic property of integrable systems is that when you take so it can be described in terms of scattering process. So you take a lot of particles and kind of make them scatter to each other, interact, and all that. What you see at the end is that all the particles have preserved their momenta. And the whole scattering, so the phase shift induced by this whole scattering, can be described by simply considering a set of two-body scattering processes and taking the sum of all the phase shifts. Okay? So this is the basic property of an integrable system. And what it says intuitively is that actually all these momenta are like conserved quantities. So if you take your fluid cell and kind of take it out of the system and let it expand and see what the momenta are, well, these are conserved quantities of the system. So you can take that as your local conserved quantities and construct then a phase space, like in free system, a phase space conserved density, for which you can try to write a hydrodynamic equation. Okay? So these thetas replace the I. So instead of momentum, energy, and density of particles, where you have theta equals 1, 2, 3, 2.5, all the possible real values. So that's what we think. For instance, the Liebninger quantum Hamiltonian is integrable, and it can be solved by Bethe ansatz. And in the end, these thetas representing asymptotic states and parameterizing your conserved quantities can be thought of as the quasi-particles of the Bethe ansatz solution. Okay. So you write, out of that, then you can write your conservation law. So this is like dtqi plus dxji, okay? Except the I are all the thetas, which are the quasi-particles of the Bethe ansatz solution. In particular, from this rho, which is the density now in phase space of integrable system, you can construct all the important physical quantities, such as the density of particles, momentum, energy, and the higher conserved charges admitted by the Liebninger model. The Liebninger model has infinity of conserved charges. They can all be written in terms of densities in the Bethe ansatz phase space. Right? In this equation, of course, there is the current. So there is a density and there's a current. There's this conservation law. And the current, well, this is the thing that is at the basis of GHD. So and it satisfies a linear integral equation that knows about the density of the state at this point xt within that fluid cell, and that knows about the interaction. Here, the interaction is denoted by this quantity delta. Okay. Where does this linear integral equation come from? Well, it's something called the collision rate ansatz. So if there's a semi-classical picture that allows you to calculate what the current is, and that gets this, brings out that formula. Okay. So this is the basic fundamental equation of GHD at the Euler scale without external force. Okay. So just to remind, so what is this basic collision rate ansatz picture? Well, you know that in an integrable system, you can divide everything into two-body scattering. So you consider the quantum two-body scattering and make a semi-classical analysis of that. So if you take the derivative of the phase that appears exponential, semi-classically thinking about kind of wave packets hitting each other, that would describe the shift of the wave packet in a two-body scattering process, a bit like a solitone shift. Okay, so this delta is the semi-classical shift. Okay, and the current is just obtained by accumulating all these shifts in a gas of particles. If you do the little analysis, kinetic analysis of that, you get exactly the linear integral equation for this effective velocity. So essentially, in an integrable system, instead of writing this basic equation of Euler hydrodynamics, you rewrite this in terms of a completely general set of Euler hydrodynamic equation for a general set of conserved quantities, and you specialize these conserved quantities to the conserved asymptotic momenta of beta ansatz, and get then an equation of the type of a free model, so a conservation law in a phase space, but for a non-trivial current, which is depending non-linearly on the density of particles. So this is for the GHD at the Euler scale without force and without diffusion term. How do you add force and diffusion term? Well, let me get to the general equation of that. So now let's consider a more general situation where you have a Hamiltonian that has as many external fields as you want. So you can think of that as some basic Hamiltonian plus coupling with external densities, whatever the external densities are. In fact, a nice example of this is when the coupling is to the energy density itself. So take your Liebniger model and change the overall coefficient of the whole Hamiltonian density and make it space dependent. It should be space dependent on large enough scale so to have hydrodynamics, so make it space dependent for an arbitrary function, W of x. That's an example. Okay, or you can think of something more general where you couple with other conserved quantities and all that. Okay, and the question here is, what is the equation that emerges in this situation, and can you write it in particular for the Liebniger model for the integrable systems? Okay? So in order to do that, you need to describe the evolution with that Hamiltonian. Now that Hamiltonian involves in general a whole bunch of conserved quantities. Okay, here is the energy density, but you can involve the particle density, the momentum, the higher conserved charges of the Liebniger model. So you need to, technically what you need to have then, you need to consider what is called the generalized current. So essentially every conserved quantity in the Liebniger model, they all commute with each other. They can all be thought of as generating some kind of time evolution. These are the generalized times or the hierarchy of times in integrable systems. And for every conserved quantity, there is an associated whole set of currents. So there's a conservation law and a certain set of currents. And from these currents, then you can consider the generalized Onsager matrix, which is very similar to the usual Onsager matrix that was written some time ago. This is a Kubo type of formula for the usual Onsager matrix, but you just put the generalized currents in there. And again, by PT symmetry, this is a symmetric matrix, and it satisfies a lot of important property. Okay, and it turns out that with this object, we can indeed write the general hydrodynamic equation for any many-body systems within external force field as described by this Hamiltonian. Right? And the equation is a bit complicated, but it takes a form that is similar to what I had written at the beginning. So there's a conservation, there's some densities of particle, momentum, energy, and other higher conserved quantities if you have them. And there are some currents, and you have an equation for conservation of these currents plus breaking due to an external force field. Okay. So what do these equations involve? Well, they involve, in particular, 4 different Onsager matrix terms, 4 different second derivative terms. One of them is actually the usual one. So if you specialize to just coupling to the particle density, like in the usual equation with the force, you get that term and the other terms go to zero. But the other ones are additional terms that correspond to additional modification of the currents. So the current is modified by additional second derivative terms, so the derivative of the external potential, and additional breaking of the densities due to the external force and the derivative of the local state. Right? So there's so these are the most general equation in hydrodynamics, no matter if it's integrable or not, for a system which is where your Hamiltonian is in general space dependent, so involving all the possible conserved charges available. So a typical example is indeed that one, which is which gives rise to new equation, non-trivial equations. Okay? Now, so these equations, because of the structure of this Onsager matrix, satisfy a lot of properties. If I have time, you say 5 minutes maximum, right? So, 2 minutes, yeah. So it can be derived by looking at the fluid cell idea, where you just do a perturbation theory by taking your force and your local state all the way up to the linear level. So you consider constant force and a ramp initial state. And from that in perturbation theory, you can describe local relaxation and get this equation. So what I wanted to say at the end is, so these equations, because they only involve the Onsager matrix, which is a positive, generalized Onsager matrix is positive, that implies that these equations give rise to positive entry production, and also that the thermal state is a stationary solution to this equation. So they make physical sense. You can write them for integrable systems, and that's the equation for phase space evolution of your in your quasi-momentum phase space of integrable system that involves both the external field with the force term and the diffusion due to external field and to the variation of the local state. And in fact, it has a structure which is very interesting, which is not a priori obvious, of still a conservation in phase space. So we know that external force would break integrability and would break break the conserved charges. And so, you know, the external force is a modification of your hydrodynamic equation, which is not a total x derivative, but it turns out that it's total theta derivative. So you have conservation in phase space. And some other interesting thing are that, yeah, so the diffusion can be calculated exactly using various aspects of beta ansatz. In particular, they involve two-body scattering of collective modes, except for the last one, which may involve infinitely many body scattering. Okay, so that's how I wanted to say. So there's a lot of things that have been done in GHD. Don't want to go all over that. And there are a few open questions, in particular with respect to the previous talk. Super diffusion is the case where the Onsager matrix is infinite. So if you try to write this two-point function of two-point coefficient function of currents and try to evaluate the large time limit, you find infinity, and so all this has to be modified a bit. In fact, it's not really known how to modify that properly when you have infinite Onsager matrix to have an equation that would describe hydrodynamically what happens at large space-time. And there are many other questions. Yeah. So thank you for your attention.